Hello everyone, and thank you for coming. My name is Svetlana Barkanova. I'm a physics professor here at Acadia, and right now I'm going to give you an introduction into nuclear physics in just 10 minutes. Nuclear physics is the physics of atomic nuclei and their interactions. Why study nuclear physics? Well, because it's fun, and because nuclear physics is serving our society in so many different ways right now. Applications include nuclear medicine, industry, consumer products like smoke detectors, scientific research like radioactive dating, and of course, energy. And apparently fashion. And by the way, it is pronounced nuclear, not nuclear. A nucleus consists of Z protons and N neutrons. Protons are positively charged, neutrons are neutral. An atom is neutral. Together, protons and neutrons are called nucleons. Z protons and neutrons will give you A, mass number. For example, lithium nucleus consists of 3 protons and 4 neutrons. Atomic sizes are on the order of 1 angstrom, 10 to the minus 10 meters. Nuclear sizes, 10 to the minus 15. This is like comparing a blade of grass to a size of a football field. A nucleus is much, much smaller than an atom. What holds a nucleus together? The strongest interaction of them all, strong nuclear interaction. And comparing to 4 fundamental interactions, gravity, weak nuclear, electricity and magnetism, strong nuclear interaction is the strongest of them all by far. But it is also extremely short-ranged, just about 1 Fermi, that's it. Now, on the scale of energy, it takes about 13.6 electron volts to remove an electron from an atom. To split a nucleus apart, let's say helium nucleus, you would need 28 millions electron volts. Millions. Let's compare the mass of parts, 2 protons and 2 neutrons, with a mass of helium nucleus, also called alpha particle. The difference is tiny. Here is 4.03 versus 4. But that mass difference can be converted into a huge amount of energy. How do we access that energy? 2 ways: fission or fusion. For fission, you're starting with something quite massive like uranium or plutonium, heat it with neutron, a nucleus will split, releasing energy. Fusion is an opposite process. You start with something very light, like deuterium and tritium, fuse those together, and again energy is released. Where does this energy come from? From binding energy per nucleon, which is different for different isotopes. For fusion, you are right here. You're fusing lighter nuclei into something more massive, and you are gaining energy. For fission, you are on the opposite end. You're splitting a massive nucleus, like uranium, and you're gaining energy this way. If you look at energy conversion per kilogram of fuel, for fusion, you can supply 676 people for a year from 1 kilogram. For fission, 176 people, which is still pretty good. Uncontrolled fission is relatively simple. You just get enough fuel together. This is the first nuclear bomb ever tested, gadget, 20 kilotons. This is a fusion bomb, Tsar Bomba, 50 megatons. So that's fusion, which is more powerful. I'm not into bombs really. I'm just explaining the difference between fission and fusion. What I want is energy in a controlled and sustainable way. Here is a generic design of a nuclear fission reactor. You're splitting uranium, you control your reaction with control rods. The energy is heating water vapor, which rotates the turbine, and here you generate electricity. A generic design for a nuclear fusion reactor is about the same, steam generator, but the reactor is different. So here you would be fusing deuterium and tritium at a temperature of 100 million Celsius. And this is difficult. And we actually don't have a reactor like that yet. But we will. It is currently under construction in France. It's called ITER, International Thermonuclear Experimental Reactor, also AWAY in Latin. We are going to start the deuterium-tritium operations in 2027. It is fusion which is powering our sun. As we speak, our sun is fusing hydrogen into helium, releasing huge amounts of energy. Every second, our sun converts more than 4 million tons of matter into roughly 4 10 to the power 26 watts of energy. 1 second of sun's energy output would power the entire US for 9 million years. The bigger stars can do even more. They are fusing everything in their cores up to iron. And then supernova will do the rest. Most elements in your body are made inside the supermassive stars fusing the elements. We're all made of stardust. Okay, now let's talk about radioactivity. And I believe everybody should know at least a little bit about that. And it's also actually quite simple as alpha, beta, gamma. Alpha particles are helium nuclei. Betas are electrons. Gammas are just high-energy photons. The biggest source of natural background radiation is radon, emitting alpha particles. We normally measure the radiation dose in millisieverts. A typical chest X-ray will give you 1/10 of millisievert. The natural background radiation of our planet, depending on where you live, will be 1 to 2 millisieverts. The radiation sickness would start from 1,000. Obviously, you don't want that much. If you do have to work with radiation, how do you protect yourself? This is easy. Time, distance, shielding. Spend less time around the radiation source. Increase your distance. Or build a shield. This is me behind the shield. Now, have you ever eaten radioactive food? Yeah, sure you did. All food is slightly radioactive. For example, banana contains naturally occurring potassium-40. Just for fun, we can actually devise a banana equivalent dose, expression for ionizing radiation exposure equal to 1/10 of microsievert. Typical chest X-ray exam will be an equivalent of eating 1,000 of bananas. A lethal dose of radiation would be 35 millions banana equivalents. Well, you're not going to eat that many bananas anyway. My point is that it's not that all radiation is dangerous at all times. You just need to know. And if you want to learn more, here's a great starting point. Or, even better, take one of my courses at Open Acadia. Thank you.